Okay, so I'm going to talk today about towards automatically assessing E&E final year projects. The reason for that word towards there is because we didn't succeed, basically. So you will be probably a little bit disappointed with this talk. Yeah, I mean, no, that's not what I said. I said we couldn't automatically assess it, but yeah, okay, we'll see where we get. So I'll just start by saying this is actually work that Carla did. She's also here, but I asked kind permission to give this talk because I wanted to share it with two audiences, basically. The E&E lecturers, and there's some process engineering, chemical engineering lecturers here as well. So I wanted to share it with the lecturers, and I also wanted to share it with my machine learning data analytics class. And she said, it's fine, I can give the talk, so that's why I'm here. So the goal of this project, which she did as a structured master's project, was basically to see if we can come up with a machine learning system where we feed in a report and it kicks out a mark. Okay, and that's the overall goal, and that's what we will try to do. Along the way, we learned several interesting lessons. And with this talk, I want you to take away two things. So I'm spoiling the whole talk. I want you to take away two things. The one is that although we didn't succeed in doing this, lecturers are actually really bad in assessing skripsies. Okay, so that is the one point I want you to take away from this. And the second thing for my data analytics students, what I want you to take away from this is that it's really important to evaluate your models properly. It's really important to consider the dumb baseline, the stupidest model, the most simple model that you can use. And then the third point, it's also important to think about the ethical implications of actually using something like an automatic assessment system. Okay, so that's what I want you to take away today. And disclaimer, I'm also bad at assessing skripsies. I also forget about sensible baselines. I start with the fancy models, and I also forget to think about ethical implications. And that's Carla. She's at the back there as well, and she did the actual work. Okay, so the goal of this project was to build a system where I should start a skripsie for, I think most of you know, but the skripsie is our final year project. A student would do an open-ended engineering project with a supervisor. There won't be a clear answer necessarily up front. They will write a report. That report gets sent to examiners. The examiners examine the report and a mark gets assigned. And we call this report, we call that the skripsie. And what we want to build is a machine learning model that takes in the PDF of the report, it goes through a model, and out comes a mark. Okay. If we could do that, then it's purely selfish. It would mean that I don't need to spend time assessing skripsies if we could do this accurately. Okay, so this is the aim of what we're going to try and do. Does that make sense? Just nod. It's very simple. Okay, so how are we going to do this? We're going to follow the standard machine learning pipeline, which is illustrated here. Okay, so what we want to do is we want to end up with a model where we can feed in a report, which I will denote as X. The report goes into the model F, and out comes a Y. That's the predicted mark. Inside the model, there are some parameters that we're going to tune, and that's, I will just denote with with little fat W. Okay, so this is a vector of all the parameters. Now, before machine learning, we would write this function or this model by hand. Trying to figure that out, that's really difficult. So the machine learning approach is instead to collect a data set of previous skripsie reports, where, so we've got capital N of these, we've got the previous report, and we've got the mark that's assigned to that report. And instead of hand coding F, we will use a learning algorithm that basically wiggles W so that you get correct predictions on your training data. After you've trained your model, okay, so that's all on the training data. After you've trained your model, then what you want to do is you want to give it a new skripsie year, and you want to get a predicted mark for a skripsie that wasn't in your training set. That's machine learning 101. So for this project, what we did was we collected 516 skripsie reports from 2017 to 2021 with their marks. We then anonymized the PDFs, which meant we removed the front page and the acknowledgements so that we don't know who the student is. That's really important for ethical considerations as well. We also noted the supervisor and the examiner, but we assigned those unique IDs as well, so that was also anonymized. Okay, so but we know this report was supervised by ID number 5 and examined by ID number 43. Okay, and we then split the data into 2 sets. The training data, this is what we will fit our model on, and that comes from 2017 to 2020. So we take all the reports from 2017 to 2020, and that's what we're going to tune our model with. And then what we do is we pass some reports from 2021 through the model. It hasn't seen any of those reports, and we get a predicted mark. And then we compare that mark to the mark that was assigned to the skripsie during the examination. Okay, does that make sense? Bigger overall goal. What we want is we want one metric that tells us how good is this model. And for that, we're going to use the root mean square error. Okay? So I know, I mean, it looks slightly fancy. It's really not. So what you have is you've got your test data here. Okay? You've got the predicted mark from the report. That's y hat. You've got the actual mark that was assigned by examiners in 2021. You take the square of that, the average, and you take the square root of that. So, sorry, this might seem a little bit dumb because most of you would know what the RMS is, but if you don't, electrical engineers, you can think of y minus y hat as an error voltage. The voltage is between 0 and 100, that's the mark, okay, and the E is just, you've got the RMS value of your error signal. If you're in statistics, this is an estimate of the standard deviation, and so you would know what that means. For today, what I want you to think of is that if we have a RMSE of 15.3, what does that mean? It means that most of the model's predictions, y hat, is within 15% from the mark that was actually assigned. Okay, so that's how I want you to interpret this, this number that we will get for different models. Lower is better, 0 is perfect, but what I want you to think of is if we have a RMSE of this, then it means that most of the predicted marks are within 15%. Okay, now I will pause here and I will just give the lecturers a chance to just tell me, what do you think when you assign a mark to a report, how close do you think you are to the, let me put this in quotes, true mark? Are you within 5%? Are you within 10%? Are you within 20%? 10, within 10? Is 10 good? People are nodding. Huh? There is no true mark. I actually agree with that. But, okay, there are some people with a belief in an underlying mark. Johan de Pre isn't here. Okay, so anyway. There might be some true underlying mark, and we don't know the distribution of that. Okay, but blah, blah, blah. Okay, so that's an interesting observation, and we'll look at that a little bit. So there's weird things that happen at the edges. It's okay. We will see. We will look at that as well. Okay, so I got a rough estimate. We agree that 10, RMSE of 10 is maybe reasonable. Okay, cool. Let's start. The first models that Carla trained. So what we started was basically the big neural network route. Okay. And this is a cartoon illustration of the whole pipeline, so all the models doesn't fit directly into this. But what we will do typically with the neural network model is we start with our report. We pass that through a Linux tool or a Python tool that converts the PDF to text. That text will be fed into a very big neural network model, typically something that's pre-trained on Wikipedia and text from the internet. The problem is that most of the reports are actually larger than what most of these models can produce. So the model will produce intermediate outputs. Maybe you feed in the whole report and you get 10 vectors out, basically summarizing chunks of the report. And so the approach that Carla used was to then feed in these maybe 10 vectors into another model, a final model, that kind of bunches those marks together, or those continuous representations together, and then outputs a single mark. And this was a RNN LSTM. Yes, boss?
Sorry, this does not include images at all. So if someone has a very pretty flow diagram that explains something perfectly, then...
Yes, okay. It doesn't include any images in this pipeline that I sketched here, but I'll say something about that in a second. So this is the kind of the bigger level picture. Some of the models would actually process images, and some of them will just work on the text. So Carla specifically looked at 2 models. You can see I'm quite nervous because I actually have talk notes. She looked at a long former, which is a text-only based model. She used a pre-trained model from Hugging Face, and then she only trained this final model. So that model would be fixed, and that pipeline would all be fixed, and she only trained this model. The other model she looked at was Layout LMV2, which actually processes the images of the PDF. So it takes the whole page in, and it actually processes that, okay? She also got that model from Hugging Face, and that model outputs a prediction for every page, okay? And then that would get fed into a downstream model and summarized into a single mark, okay? And that model can, in principle, take into account images. Okay, so I'll give the scores here. Remember, you are aiming for an RMSE of 10. Congratulations, okay? So let's just look. So the long former, which is a pre-trained model, 52,000 parameters into this final thing, gets an RMSE of 13.01% on the validation data, okay? Layout LMV2, she started with a pre-trained model, but she backpropped through the whole thing, updated that as well. It has 200 million parameters, RMSE of 13.14%. Okay, cool. Looks good. Okay. We obviously analyze these models a little bit. So machine learning people, you know, you look at your training loss and your validation loss as you're training this thing. Very smooth curves. Incitement builds on the inside. Makes us like really, really happy that you've got these smooth predictions. So as you're training the model, it comes down. Now, the interesting thing that she then did was we actually looked at the predictions of the model for different inputs, and we observed something really, really interesting. This model outputs the same value for any input. It outputs a mark of 67.03% for any input. Okay, same mark. Get an RMSE of 13%. Okay, cool. So we've trained, in the one case, a 200 million parameter model to learn one number, 67.03. Okay, so it turns out in machine learning there is a simpler option than this. Yeah. Yeah. Okay, there is an underlying model, exactly. So it looks a little bit simpler. So instead of 200 million parameters, we have one parameter, W0. And this is actually in statistics called the null model. Okay, and what is this model? It's the average of the marks that were assigned between 2017 and 2020. Okay, so what you do as a lecturer, you get that average mark, and without looking at the report or opening it, you give a mark of 67.06%. You get within RMS. You get an RMSE of 13. Okay, this is great. Okay, so the neural model does something. Okay, this is within the bounds of noise. The concrete number here is 13.17. Okay. Okay, cool. So the moral of the story for my data analytics intro to machine learning students are, if you're going to use a big neural network and it seems to work, also just ask what the really, 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 really dumb model would do. Okay, so just compare it to the simple. Dumb is a strong word. Compare it to the simple model as well. Okay, so why does it work so well? And some of you have already hinted at this. If we look at the training set, the marks assigned to our skripsies, so this is just for the training set, you will see that actually most of the marks are between 55% and 80%. That's the bulk of the skripsies. So 67, wherever that sits, 13 plus 13, minus 13 plus 13, the bulk of the marks are in that. So most of our marks are here. It's interesting what Dirk observed earlier, that you've got this boundary effects at 75, for instance. So you've got this big jump to 75 because often when a student is like at 72, we push it up to 75. So you do see that type of thing here. Fails. Okay, yeah. So, okay. So now that the goal of the project, which we initially set out to be this neural network model, will now be to beat the null model. Okay, so it changed quite dramatically. So what we do is we turn back the clock and we go back to old school machine learning. And how this works is you have a problem, and then you think, what are the features that are meaningful for predicting a mark? Okay? Neural network land, you have the model actually figure out those features internally, and we saw that that kind of failed in this case. And in old school feature engineering, you come up with these features by hand. And then you feed those features that you came up with into a simpler model, maybe a linear model, or Carlo also tried a 2-layer neural network, which then outputs the mark. So, same kind of pipeline. You start with the reports, we extract the text, and then from the text, we think, what are the types of things that can influence the mark? So there's a whole bunch of things. Number of words, maybe the number of figures, the number of spelling mistakes, and so on. And that then gets fed, this vector then gets fed to a linear model, and the mark comes out. Does this make sense? Okay. So Carla thought up a lot of features, and we had a lot of very interesting meetings every week thinking of different features that we can add to this model. So I don't want to go through all of them, but you can just see there, so just focus on the Python environment part. So things like number of pages, word count, number of spelling mistakes, that makes sense. Number of spelling mistakes types, so that's the unique. If you spell the word wrong twice, then it only gets counted once in that second and that fourth feature. You can go down, 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 down. Some other interesting features, supervisor ID, who supervised it, examiner ID, who examined it. Important features that we'll get back to. The one other feature, this is actually 10 features, which will feature again later on, is we took the 10 content words that occurs most often in the combination of all the skripsies, and you count. So the word, can't remember exactly, word 7 was voltage, okay? And you count how often does voltage occur in this report, and that becomes another feature. So there's actually 10 features there. You can go down here. Now on this side, what you found very interesting, we all hate Microsoft, but Microsoft Word has a very cool feature where if you plug in text, it actually analyzes the text, tells you, basically gives you a score, gives you the number of spelling mistakes, the grammar, and some metrics on basically telling you how well you're writing. I'm just going to take a sip. Okay. Okay, so what she did by hand, this was quite painful, was she fed all of the stuff into Microsoft Word, and then by hand, I think you did it by hand, yes? By hand, she cut it out and basically put it into a big spreadsheet, and that became additional features. Now, there's a lot of features here, so we learned that simpler models are maybe a good place to start. So the first thing she did was she just trained a linear model on each of these features separately, okay? So this is, there's one more feature that I need to talk about. This is an interesting feature. Okay, let me talk about it. So this is a feature, what we wanted to do, we also wanted to capture the topic that the model is, that the report is assigned to. Like, is it in electromagnetics, is it in energy, whatever. But we didn't want to define those topics by hand. So what she did was she took the complete set of reports, and she feeds that into a topic extraction model. It's more or less a model that sees within this document, these words are often used together. And from that, you automatically, without actually having to define it, you come up with topics. You don't know what these topics are, right? It's just topic 0, topic 5, or whatever, but you can see what it extracted. So just going very quickly, system, data, sensor, network, temperature, server. Not exactly sure what that is, with some computer systems, skripsie. The second one there, antenna, method, frequency, that's an electromagnetics topic. This one is a control systems topic, power, voltage, design, generator, synchronous machine. That's an energy machine topic. That one is machine learning. This one, satellite altitude, so it's a Willem Jordan Herman Stein topic. Energy again, and this is a Jaco Versveld topic. Okay, so this was fed in as an additional feature into the model. But we start out simple. All we do is we take each feature in turn, and this is our null model. What we do is we just add one feature to the null model, okay? And aim of the game is to beat the null model, okay, in terms of RMSE. So what you have here, that first line, that is W0 plus W1 times the number of pages. Boom, you get an RMSE of 12.58. Okay, so slight improvement over the baseline model. Number of words in Python, you extract the number of words, 11.49. We're getting close to the 10 that you said you are aiming for, okay? You can read through these. It looks reasonable, and we're a little bit excited because we're outperforming the null model here. Okay, cool. There's a lot of features. So what she did was, instead of training on all the features together, you used techniques to basically reduce the set of features, feature selection techniques. And she looked at two techniques, mutual information and lasso regression, which are two approaches to get a subset of the features that are most meaningful. So now we're training a model W0 plus W1 x1 plus W2 x2 plus W3 x3, and that's in the linear regression case. In the neural network case, he feeds in a few more features, but it's a nonlinear prediction. Okay, baseline 13.17, that's the null model, and you can see with some very slightly more sophisticated feature selection techniques, we can get maybe a 10.11. So there, we're getting very close to our 10. And then I forced her to always report the word count model as well, because it was my personal favorite model. So all you need to do as a lecturer is open it up and count the words, and then you can assign a mark. So I really liked that model. So I forced her to do that. So this is just on the validation set. Test it. I'm not going to talk about this, but basically in machine learning, you split your evaluation data into two sets. You tune your model on one, the validation set, and then for a small set of models, you also look performance at the test set. This is probably too many test set results, but I think it's okay. We got really frustrated because it seems like the test set. So it was actually 2021, but we split 2021 into two groups. And it seems that the second group, for some reason, so if your name is later in the alphabet, it seems that our models actually do even better on that set. Okay, so this was a little bit earth-shattering to us, right? So with a massive amount of hand engineering effort, you can start to get models which maybe looks sensible. But this might just be a very, very difficult task, okay? And the question then is, how well can we expect a machine learning model to actually do on this problem? What is the best possible performance, okay, given the training data? And the answer to this question is, have the people that gave you the training data also do this task, okay? And what does that mean? So what we did was, I sent out an email to my colleagues, and what we're going to do is, we have an approach to get a y-hat out, a prediction for the model. What we're now going to do is we're going to see how human experts do on the same task, okay? So what we did was we got a bunch of lecturers. Some of the lecturers kindly agreed to re-examine skripsies from 2021. So we've got our validation data from 2021. We're sitting in 2022. These lecturers go and remark skripsies from 2021. We asked them guess the final mark that was assigned to that skripsie. And that's now our new model, y-hat, okay? And we're going to compare the predictions from these re-examinations to the predictions from our models. Does this make sense? Okay, so this is the upper bound. You cannot do better than this because the training data actually came from these people, okay? Which includes me, sorry, okay, from us. Yeah. It's a random selection, so we did a random selection, but I think in two cases there were examiners that examined stuff from before. Out of all the re-evaluation stuff, there were two, and I think the marks were within 5% of what was actually assigned. Okay, because we want to quantify what is the upper bound here. How well can you get, and because you can't ask a machine learning model to accurately predict noise. Right? And we want to get an estimate of the noise in this problem. Okay, now this is an enormous table. Sorry for that. For my postgrad students, bar graphs, right, is what you need to do, not this, okay? But let me just talk you through this slowly. Forget about this column here for a second. We're just looking at this column here. So let's just look at this one. My favorite model, word count. It looks higher because the subs we had them. I don't have enough friends, so I didn't have enough lecturers label the whole validation set. So it's a subset of the validation set that was labeled. So the scores look slightly different from before. With the word count model 13.73, our null model does 14.73. And the lecturers got 12.21.
At least we did better.
Huh?
At least we did better.
At least the lecturers did better, yes. That's true. Okay? So they did slightly better than the word count model. It is interesting if you look at the neural network with mutual information selected features, 11.19, which is better than the lecturers. Okay? Which is weird, right? So this means we're in the area of the noise of the model. We're not exactly sure how these predictions are being made. Carla also had her friends actually examine these anonymized skripsies, and you'll be very happy to hear that their friends got 15.03. So non-experts are worse than the lecturers, which is pretty encouraging. Okay.
Was the non-experts engineers, or were they anyone?
The non-experts were mainly applied mathematics structured master students.
In the set environment.
Oh, am I allowed to say this? I'm recording this thing. Yes, they would, like, in the technical.
So they could understand.
Yeah.
To a certain extent.
Yeah. Some of them were more diligent than the others, but I mean, even with the experts, we had the same problem, that some of them were really good and some of them were not as good. Now, okay, so this is root mean squared error, and I just wanted to put this up here as well. This is mean absolute error, so it's a different metric. So you basically take the difference between the predicted mark and the real mark, and you take the absolute number, and then you take the average, okay? Now, what mean absolute error does differently from root mean squared error is it has a linear penalty on the mark that you assign. What this means is with root mean squared error, if you make a large mistake, it's penalized more than a small mistake. And so this was interesting because if you look at the mean absolute error, actually the lecturers do better than any other approach. And what this tells us that, and you could see this qualitatively if you just looked at the marks, when a lecturer makes a mistake, it's a big mistake, okay? But like at the smaller range, lecturers are pretty good, relatively good, okay? But you would see this, you would have one lecturer get within 5%, within 5%, within 5%, 30% out. And this is captured in that metric. Okay.
Sorry.
Yes?
Is this also true from individuals?
Huh?
So it might just be like outliers on an individual level.
Yeah.
Like it's an individual. It's a single lecturer that's really bad.
Okay. So let's just. The single lecturers gave the training data, right? And this is what's on the student sheets, like when they graduate here. Yes, but yes.
For the error, for this human error, you still use the original mark as the answer, as the correct value.
That's right. So the mark assigned in 2021 that is the target, okay, which is also like both of these measurements are actually noisy, right? Yes.
So those marks are usually
averages.
Yeah, they're assigned after a discussion between two examiners.
That's right.
So usually that's also the average between two marks.
Yeah. So I tried to get the individual marks. It's actually quite difficult because of the way that we store things. But it is a good point that there's actually a discussion between the ground truth here is the discussion as a mark assigned to two examiners discussed afterwards. So one of the, maybe I shouldn't say who re-examined stuff, JC was one of them and he was pretty close on most scores. And he said, this is the mark that I would have given for the report, not after the discussion. So maybe that's something to quantify. Jamie, yeah? Yeah. Option 2, we don't have a rubric. There's a oral discussion. There's an oral discussion, 2 reports comes in, there's a convener, and the average of, well, no, it's not the average of the 2 marks. A discussion takes place, and that little panel decides on the final mark. Okay, so when we set out this project initially, when I applied for a little bit of funding and got help from Corin, what I promised was oh, even if it doesn't work, we'll be able to get a system that can tell us something, maybe help students write better reports or tell them what we look at when we're assessing reports. So I know there's a lot of slides left, but the slides at the end are pretty short. So I just wanted to show you this. So this is what you do if you look at the inside of the model. Okay? So we've got a trained model, and now you can see, okay, based on what do you make your prediction? Okay? And so the first thing, I think this is just the simple linear regression models. So here we've got the topics there, which the discovered topics, and then the marks that gets assigned if your project is in one of those topics. And so this is quite interesting. Let's just look at the highest and the lowest. Antenna method frequency results is electromagnetic. It's a high mark. Okay, the other very high one, with model learning, neural, machine learning gets very high marks. Bad marks, system design, data radiation, that's the satellite and control system topic, very low mark. Okay, so you see these differences, and you can actually see this from the model coefficients, those parameters, the weights. I should say with machine learning, there was one outlier data point, because a student in that 2017 to 2020, there was one student that got 100. So there's some bias in there, but okay. You can also, if you have a linear model, then you can look at the coefficients for each of the features. So this is a combination of all a whole bunch of different features, and a large positive or negative coefficient tells you something. Okay, not everything, but it tells you something. So you can see what this means is characters. If you have a lot of characters, it has a large positive weight, so you will get a higher mark according to the model. If you have count 8, so this is the count of the 8th most common word in all of the reports, then you get a higher mark. I'll tell you what that name is in a second. If you have more figures, higher mark. If you've got poor grammar, that's a Microsoft grammar score. If you've got poor grammar, lower mark. If you have and so this is important for all my students. If you write paragraphs with a ton of sentences in them, you get a lower mark, okay, which makes sense. One paragraph, one topic. Okay, and then count 7, also negative mark. So count 8, the word that occurs 8th most common in all of the reports is the word N. Okay, it's actually the mathematical symbol N, which is in machine learning very often used to denote the number of training items or validation items. So all that count 8 says is if you're in machine learning, then you're probably getting a slightly higher mark. Count 7 is voltage. So if you use voltage very often in your report, slightly lower mark. Okay. You can also look at the predictions from your model. So you can see the training data is kind of all over the place. So here we've got a linear model, and we've got our neural network. On this axis is the number of pages, and on that axis is the predicted mark. So what you see is, even though we've got a cap on the number of pages, if you write more, if you have more pages, then you get a higher score. With the neural network, which is slightly more accurate in this case, you see that it plateaus out. So you need to write at least 60 pages, and then after that, it doesn't help you that much. Okay? The page, what is the page limit? 6. Okay, it's very clear that neither the lecturers or the students know the page limit from the discussion here.
Did you add the dependency?
Yeah, so this is important. This is the PDF. This is the PDF pages. So this is the body with the appendices. Okay, so more pages generally better. Now,
sorry, so we actually had one scripsie including appendices of 16 pages.
yes, it's fortunate it got a mark of 40. Right?
That's quite close actually to 50.
Is it? Yeah. Okay. Cool. If you look at the number of words, it was kind of interesting. Number of words, more is just better. Okay, it's a very linear model. Now, I think the reason for that is that one scripsie there, okay, which had a ton of words and got a mark of 100%. I hope it's okay, Matthew, that I tell them that that's your scripsie. Now, what Matthew did was he looks at rules very carefully. So if someone tells him write 60 pages, that's what he does, right? But he managed to fit in more words than anyone else into 60 pages. Okay. So, okay.
Small words. Small words.
Small words, a lot of appendices, okay. I can spend a lot of time on this slide, but it's not as interesting as you would hope. So this is the examiner ID, but since we don't know who the examiners are, it's actually quite difficult. But you do see outliers. So examiner 0 is 58, and what Carla did here nicely is she just reported the number of words on average that lecturer examined as well, so that you can, because we now know that more words, higher mark, so you could kind of compare the two. And you can see that there are kind of offshoot examiners. So there, examiner 24 is super strict, okay? This examiner, 45, I don't know who this is, but they're way too lenient because their reports are relatively short that they examined, but they gave massively high marks. Okay, so if that examiner needs to like contemplate life a little bit, but so you can do this type of analysis. There was one ID that we didn't obfuscate, and that was me. But I can't remember what my ID was. Carla, can you remember? Okay, all I remember is Carla telling me I'm too strict because my marks, the reports that I examine are fairly long, but the marks I assign is too low. Okay. It's really crucial, and I want to stress this point, that correlation, which is everything we've done up to this point, doesn't mean causation, okay? And what I mean with this is some of the skripsies students here might walk out and just say, I'm going to write a really long report with a lot of words, and that will give me a higher marks. That's not what this says. Up to now, what we've seen here up to this point, what it really says is that to predict the mark, we can use the number of words as an indicator, okay? Now, the bullet points on this slide is not true, but it's causal reasons that still fits this data. So it might be true that better students who will get higher marks, they just end up using more words. If you're not a good student and you now use more words, you're not guaranteed to get a better mark, because then you make the correlation causation mistake. Of course, what I'm doing by giving this talk is I'm actually intervening now, and that could actually mess things up. Because that's how you measure causation. You actually need to do something and then see if things change. So two other reasons that still fits the data. The smarter students might just be selecting machine learning topics, and the dumber students do control systems and satellites. This isn't true. We do not know. We do not know if this is true, right? But I'm sorry. We don't know if it's true. But it's causal. It's like one argument that still fits the data. Okay, so all of that to say, and I think one of the external examiners really made this point, that you need to think very carefully whether we would actually use a system like this to award marks. And obviously, we will not. You can't just take the number of words and based on that give a mark to students. So it's almost certainly not a good idea. So what do I want you to take away from this? I just want to emphasize here, this is a joke slide. So only the first bullet on the slide is actually a legitimate thing that you should take away from this. So the first bullet is, lecturers, you are really bad at this. Okay, that is true. Now our joke, if you are unsure, give 67.06%, okay, in the examination. It's a good approach. By saying that, I'm making the correlation causation mistake, okay? So it's a joke. Students, bunch of jokes, ignore page limits and write a lot, but after 60 pages, it probably doesn't really help. Pick topics in machine learning and electromagnetics, you will get higher marks. Again, that's not true, because it might just be that the best students are in electromagnetics or whatever. Okay, so we've ended like this whole study, and I guess the big question is, what should we do next, or should we do anything with this study? In the short term, what I think we should do, if we get a little bit more funding and help from the supervisors, are that we should maybe extend the human evaluation setup and to really quantify how bad are humans, because the lecturers labeled a relatively small set. I think it was interesting from the discussion as well, Willie made the observation, so that our training data is actually bad, right? And that's a polite way of saying E&E lecturers are bad at assessing skripsies. And the question then is, can you build a model that helps lecturers become basically improve the gold standard of the scriptsy reports. And I think that's maybe an interesting like medium term, like a 2-year goal, to try and see, can we actually build systems that help us examine things better? And then I think this is what I pitched to Karen right at the beginning, but I think maybe it's not something we should look at in the near term, is a system that can help students actually write better reports. The reason why I'm saying I don't think we should focus on this is that there's many companies already doing this, and like Microsoft Office, this thing we hate, already gives you actually pretty good feedback. Okay, Grammarly is excellent in actually like rating your writing and telling you, oh, this is too informal, this is formal, and so on. So I think there's a lot of good tools already. We should just get students to actually use them. Okay, so I will end there because I just want to leave some time for discussion. But I should acknowledge Carla, who obviously did most of the work. Leanne, who helped, she's not here, I think, but she helped with some of the data collection. I paid Leanne with money that Karen got for me, so Karen, thanks a lot for helping with that. Matthijs, Thomas, and Arnold, none of them are here, I think, but they were all previous year Scripsy coordinators that helped to get the data. And then the lecturers who reassessed things. Sorry, I named JC. I had everyone's names on here, but then I removed it. The rest of you, or the chemical engineers, or the applied mathematicians might just be better. Okay, that's the end. Is there any questions? There was one question that no one asked that I really wanted someone to ask, which is the question like, my whole inbox is full, is what does ChatGPT do on this thing, right? So this morning I fed in only the abstracts to ChatGPT. I gave it the prompt, give the following abstract a mark out of 100. It needs to clearly define the problem, motivate why it's important, describe the approach taken, and state the findings. Here is the abstract, and then I would put in the abstract of each of the reports. The RMSE is pretty horrible. But it gives, I think it's related to what Dirk said, it's biased towards very high marks. So there were a bunch of 80s and 95s. I think if you normalized it, it would probably get a better mark.
Also, if you asked, this is on the university level or on the high school level, that would obviously.
Yeah, so there's a bit of, like, I only had 30 minutes, so what Renzo describes as prompt engineering. I need to come up with a better prompt. This was bad, is basically what he's saying. I tried a few different ones, and then this one was the one I stuck with. Okay.
I just want to say I'm relieved that we're still far from replacing Dexter.
Yeah, maybe.